Hello there, my name is David Decatur. In this video, we're going to take a look at how to add currents in a parallel circuit consisting of a resistive load as well as an inductive load. So we're going to start very basic. Pure resistive load and a pure inductive load. We won't mix any of the RL single branches or capacitive yet. Let's keep it very basic, right? So we've got 10 amps through the resistor. We've got 5 amps through the inductor. So when we take a clamp-on ammeter, this is what we're measuring. This is 10 amps RMS and 5 amps RMS. And what we want to figure out is when we measure from the source, what is it that we're going to find? It won't be 15 amps. It's going to be something else. So where does that come from? We've got to remember a couple of things. So when we look at the current of the resistor, it's in phase with the source voltage. So if this is my source voltage sine wave, my current is going to be perfectly in phase with that. And that's going to be my I of the R right here. All right, so when we go ahead and plot that in a phasor, then it's going to be perfectly in line with our voltage here. So that's the I of the R. All right, so no phase displacement between voltage and current with a resistive load. However, when we get to the inductor here, the inductor we know typically current's going to lag. So current has to be falling behind. So it's this one being a perfect inductor without resistance, it's going to be 90 degrees behind. So the current is going to look something like this, and that's my I of XL. So it's falling behind. So my current here of the inductor is at 0 when my current of the resistor is at max, and my current of the resistor is at 0 when my current of the inductor is at max. So there's a 90-degree phase shift between those two currents. So when I plot that on here, my I of the XL is going to go at -90 because it's 90 degrees lagging. So that's IXL. So when I add those two together, I have to take that relationship into account and make sure I handle them at the right locations. So technically, the I of R in this case is at 0 degrees, perfectly in phase with voltage, and the I of XL is at -90 degrees, and we could say at 270 in this case. All right, so either one will work. All we got to do now is add them at their angles. So what we're doing here is I total is equal to I of R1 plus the I of XL1, and we have to do that with respect to their angle. All right, so that's what we're looking at here. Okay, so let's do that. Let's take the I of R1 and let's plot this into just a simple chart so that we can get our values of both the horizontal and the vertical. All right, so the I of, there we go, the I of R is 10 amps at 0 degrees. So we take 10 amps times the cos of 0. Well, that's going to be the full 10 amps. That makes sense, of course, as we are 10 amps on the horizontal. Should have no vertical component there. So 10 amps times the sine of 0 is going to get us nothing at all. Same thing here. We're at -90. So the 5 amps times the cos of -90 is going to net us nothing. And then the 5 amps times the sine of -90, well, that's going to be the full vertical component. So that's 5 amps, but that's a -5 amps. So it's crucial that we observe the positives and negatives when we're calculating phasors, because we will have mixed values with L and C, and we'll want them to cancel each other out. So when we look at the total here, we have 10 amps on the horizontal and 5 amps, -5 amps on the vertical. We figure out the I total. We can take the basically A squared plus B squared is going to equal our C, and that's going to be sort of a Pythagorean theorem to solve it. So 10 squared plus -5 squared, the negative disappears. What we get left with is I total is equal to 11.18 amps, and that's what we're going to measure from the source here. So 11.18, and through that resistive load, we still have a full 10 amps, and through our inductive load, we still have 5 amps. We only have 11.18 coming from that source. And why is that? Well, we just got to remember, the currents aren't flowing at the same time, so we're taking this current in here, and we're adding it to this current in here. So we just want to kind of take that into respect that we're adding currents that are happening at different times, and there's some overlap in there, and that's the total, and they're fortunately at 90-degree relationships. So it's very simple to solve for total current in an RL circuit. All right, so thank you for watching, and we'll see you in the next one.